Hey guys, welcome to another lesson. So today we continue on with the extension 1 topic of volumes. Today's questions all relate to trig type questions. So some of them are quite straightforward, like the ones I'm going to do, but also you need to be able to integrate things like cos squared and sine squared, which is very extension 1. So they're the types of questions I'll be doing with you today. Before I go on, if you haven't already done so, please hit the like button, subscribe to the channel, and tell your friends. So now, before I dive in, just to recap on some of the formulae, right, that we need to know in volumes, right? So for those that recall, I call volumes if it looks like this way, if it looks like a horizontal type curve like that. So if I said I want the area between A and B rotated, about the x-axis. Let me extend the x-axis, right? So I want this area here rotated around the x-axis. So your shape now, the best way to draw it is to basically draw an identical function downstairs. Bit of arc there, bit of a circular arc there, and then sort of pieces here. It looks like a Christmas ham, doesn't it? Right? Or spit roast, right? I call it a spit roast. It looks like, something that you eat, big leg of ham, and we rotate that into the third dimension. Now, if it's this way, right, the formula that we're going to use is volume is pi between the two limits of A and B, right? Now, normally I write function of x dx, but let's just write y squared dx, right? Same thing. Yeah. So that's the formula we're going to access now. Alternatively, if it looks like one of these kebab roasts, right? One of these donut kebab roasts. So I have a graph, let's say a function looks like this, right? And I have an offsetting one, sorry, a similar one on the left, right? And I want the area between A and B, so this area here, rotated about the y-axis, right? So this area here. The best way to draw it is this one here, similar to the horizontal one. This guy here, and sort of draw yourself like a nice kebab, right? Yeah, it makes you a bit hungry, doesn't it? Yeah. Now, and the only difference in the formulae is that still goes from A to B, but swap the x and y's around, dy, right? So they're the formulae we're going to access. Let's dive right into the question. So first past paper question comes from Caringbah 2015. Now, it's worthwhile pointing out that before the change in syllabus in 2019, so 2020 was the first year of the new syllabus, 2019 backwards, volumes was actually part of the advanced syllabus, right? So some of these questions, which are somewhat easier, like this one here, would be part of the 2-unit advanced syllabus, but now all volume questions are part of extension 1. So if you dug into the past and you're like, why are these questions all hard in 3-unit? It's because the easier ones were in the 2-unit paper. Yeah. So let's get started. So in this question, the area bound by the curve y equals a sec, right, which is a reciprocal of cos, between the limits of 0 and pi on 360 degrees is rotated about the x-axis. Cool. Now, not that you need to, but it's, oh, sorry, let's finish off the question. Find the volume of solid formed by the rotation. Okay. Not that you need to, but if you, it'll really help you if you drew a diagram, right? Yeah. So now, for those that recall, I'll just quickly sketch this. A cos graph sort of looks like that, right? And then sec, for those that remember, and all the x-intercepts, they form vertical asymptotes, right? And then the graph sort of looks like something like this, right? Yeah, as it goes on. Now, when you do this graph, the limits that they want me to rotate is between 0 and pi. Where's pi on 3 now? This is pi on 2, right? Over here. So pi on 3, 60 degrees must be about there. So the region they really want me to sketch, to rotate now, where am I rotating about the x-axis? So they want me to rotate between 0 and pi on 3. So it's just this little area. In fact, let me use this highlighter here. Just this little area here, right? So I don't actually need this part of the graph. So what I'm going to do, guys, right? I'm going to just draw another graph that's sort of zoomed in. And it sort of just looks like this, right? Yeah. And they want me to go from 0 to pi on 3, which is somewhat there-ish, right? And want this graph here, this region here, rotated about the x-axis. Now, I really don't need to do more than that in terms of diagram. Otherwise, just spending too much time on diagram. So mathematically, like the answer wise, v equals to pi between the two limits of 0, pi on 3. Now, the formula that I gave you before was y squared dx, and all you have to do, right, is sub in this function of sec x into here. Yeah. Now, if there's no squared, if I just want to find the area, the integral of sec x is actually quite hard. It's a extension 2 4-unit question. But the fact that it's sec squared when I sub it in, that's easy because that's part of the reference paper and formula sheet, right? So when I sub in sec, so this is why I love in extension 2 for those that do it, and I love integration because, sorry, that should be sec x, right? Because the difference between sec squared and sec x as an integral is massive, right? Actually, sec x, can I just say, is my all-time favorite integral. For those that know the little hack for it, maybe I'll do it in a video later. The hack for it, maybe I've already done a video, who knows, is amazing. The hack is amazing, right? So guys, we know that the integral of sec squared is tan x. So that just becomes that tan x pi on 3, 0. And then sub in your limits, becomes pi tan pi on 3 minus tan 0. Now, we know that tan pi on 3, that's like tan 60, isn't it? That's root 3. And tan 0, 0. So the answer, quite simply, is root 3 pi now, because it's volume units cubed. How's that, right? So when it comes to trig, sec x is actually really easy because it becomes sec squared, and sec squares is a integral that we have on our reference paper. Yeah, let's do another one. So the next one here is typically 3-unit, right? The first one was from the 2-unit past papers. This one's definitely 3-unit. You'll see it in the integral that we use. So area of that graph between 0 and pi, that's important to find the limits. Now they have the graph for us, makes it easier. And it tells you that the rotation is going about the x, right? I can see it there in the diagram, but it also tells you rotate about the x. All right. So once again, v equals to pi between the limits of 0 and pi, y squared dx. And in this case, the difficulty is the last one, maybe the diagram, not having diagram is a bit hard for people, but for this one, diagram's given. The difficulty is definitely in the integration part, right? So sub that in, yeah, and you get equals to pi between 0, pi. Now, I'll be good, and I'll show working out. Yeah, square that becomes 9. So I'll bring the 9 out quite immediately, right? 0 pi cos squared, right? X on 2 dx. Now, once again, I love integration because if you were to differentiate cos squared, pretty easy, right? Just use a chain rule. But if you were to integrate cos squared, not the chain rule, there is no chain rule here, right? Instead, for those that know, we access the double angle formulae in extension 1 maths, right? To do this, because I can't integrate cos squared, but I can integrate cos 4x, whatever x, right? That's pretty straightforward. So for this one, we access the fact that I know that cos double angle equals to 2 cos squared minus 1. So therefore, making cos squared theta the subject, that becomes cos 2 theta plus 1 on 2. And guys, so for this one, just to be clear, x on 2, that's theta. Yeah, so I'm going to use that formula to help me. So I'm going to go replace, that becomes 9 pi between 0, pi. And instead of cos squared, I'm going to go cos 2 times x on 2 is just x plus 1 on 2 dx. Now that's nicely integrated. Take the 2 out, right? Nicely integratable. 9 pi on 2, 0 pi cos x plus 1 dx. Guys, simple now, right? So accessing the double angle formula makes this very 3-unit because you'd only learn the double angles in extension 1, right? Yeah, because then my integral becomes integral cos is just sine. Integral 1 is x between pi and 0. Yeah. And then sub in your limits, 9 pi on 2. So sine pi, which hopefully you guys know is 0 pi. So that guy minus sine 0 minus also plus 0. So I've got this guy 0, that's pi, that guy 0, that's 0. So the final answer, so this whole thing is just pi. So my final answer there is just 9. 9 pi on 2 times pi, so 9 pi squared on 2 units cubed. Yeah. So I like that one because uses double angles of trig, right, as probably the hardest part. It's not really hard, but double angles a little bit harder than the one before, where it's x squared. All right, let's proceed. Next one. Now, no diagram, right? Makes that a little bit harder. 4 marks, Balcom Hills, right? Alarm bells, right? So let's see. I've got curve y equals 2, so that is a cos graph shifted up. And just be careful because the amplitude is doubled, right? Between x 0 and pi on 2, it's rotated about that. Now, if I was to draw a rough diagram for the next one, right? Just so I know, because just sometimes when you, say for example, if I had a graph on that and the limits was from 0 to pi here, right? Say for example, the fact that I'm rotating about a function that crosses over the x-axis makes it a bit harder and a bit more thought. But if everything's positive, life is easy, right? So let's have a look at this graph. So I have y equals to 2, so cos x, so 1 plus, so the middle point is there, and 2x, so the highest point there is 3, the lowest point is -1, and so does this, doesn't it? It starts here, and it ends here, bottoms out here, boom, boom. So I don't think I have anything to worry about because from 0 and this point here is pi on 2. They just want this graph. They want this region here rotated. Okay, so I'm sweet. Everything's positive, right? Just wanted to confirm that. So if I was to set a question in a test, I would try to sometimes aim to have an area above, an area below, and it sort of does like a rotation on both sides, just to mess with people's integrals, right? So that one there gets rotated about the x. Perfect. So then all I need to do, so I'll just quickly label this, right? Just so I can have it there. Once again, this is dx. So volume is pi between the limits of 0 and pi on 2 again. Y squared dx, right? So then sub the y, this guy, into there. Now, I think this one, once again, the intensity is the integral part, right? Because the diagram is fine. Let's see. I've got pi on 2 here, and I'm going 1 plus 2 cos x squared dx. Yeah. So where's that going? So pi 0 pi on 2. Now, perfect square comes, don't need to bracket anymore. 1 plus 2 times that, and that's 4 cos. Okay, still integratable. Plus 4 now cos squared, right? Oh, I wrote theta because I was thinking about the double angle, which I will use. Yeah. So once again, just like before, guys, cos squared x, can't integrate that immediately. Need the double angle, right? Which I know to be cos 2x plus 1 on 2, right? If you look at the previous question, which is nice because that 4 and that 2 will cancel out to something quite nice. So let's see. That's pi on 2, 1 plus 4 cos. 4 times that, so it's 2 outside of cos 2x plus 1. And guys, just to clean everything up before I integrate. Yeah, can you see that the 1 and the 2 times 1 can be collected to be 3, right? Makes it easier. So it becomes 3 plus 4 cos x plus 2 cos 2x. All right, now let's integrate. How much space do I have? Not that much. Yeah, that's fine. Yeah, let's gun it. Becomes pi 3x plus, now integrating that, that's just full sine. Now for this one, reverse chain rule, I actually have the derivative of that in front. Perfect, right? That just becomes sine 2x on 2, 0. Quick check, I think that's good. Yeah, and then subbing in all my limits. So 3 pi on 2 plus 4 sine 90, which is 1, I believe, and then sine pi, which is 0, and 0 plus 4 times 0 plus 0. Okay, cool. So the only numbers were of note is that this guy here is 1, that guy there is 0. So my final answer would be 3 pi squared on 2, yeah, plus 4 pi. I think that's it. Perfect. Units cubed. Yeah. So once again, this question wasn't hard in the diagram or interpreting the question. The intensity is captured in the sort of integration steps, right? Just be careful. Whenever there's double angles, cos squared, double angles need to be used, right? I've got one more question, right? That relates to trig and volumes. This one here is from Balcombe Hills again, 2022. So this is part of the new syllabus. So normally I found that questions when it comes to volumes and volumes, area and volumes in the new syllabus, it's harder than the ones that usually appear in the old syllabus. So let's see. So this graph, there's 2 trig graphs intersecting, and they give you where it intersects. So it tells you that the intersects at pi and 4 on the graph, right? Perfect. So I use a different highlight color. They use the same blue as mine. Okay. So that's the point of intersection. That's good because now I need to know now, what am I doing? Verify that that's the coordinate, x coordinate p is that. So I'm assuming then that I solve it simultaneously. Yeah. Or I can just sub it into both graphs and see if it gives me the same y value, right? That's probably easy actually. The shaded graph makes a revolution about x-axis. So it's rotating about the x again. Sorry, I didn't get a question that actually rotates about the y, but I mean, same. And that the resulting volume is that. Okay, cool. Part 1. Because it says verify, not find the coordinate, I'm just going to sub the x value in, and it gives me, into both graphs, if it gives me the same y value, well, then I verified it's the same coordinate, right? So for y equals to sec x, right? Y equals to sec pi on 4. Now I know that sec pi on 4 is like 1 on cos pi on 4, which is 1 on root 2, it's root 2, right? And for the other graph of y equals to 2 cos x, y equals to 2 cos pi on 4, that is 2 times. Now, another way of phrasing 1 on root 2 or cos is root 2 on 2 if you rationalize. That's nice because then 2 cancels out. Yeah, they both share the same y value, therefore x coordinate of p is pi on 4, right? Same. Yeah, that's all you need to do. All you need to do. Now, part 2. So for this one, we have to find, so the way you sort of see it is, if I take that blue area and I rotate it about the x value, there's like a gap in the middle, right? Another way to do it is you basically rotate the volume from this line here, right? And then you rotate the volume from this line here and you subtract it, right? So you rotate the y. So you rotate the y value from the pink, and then you rotate the y value from the blue, and you subtract the volumes, right? So you basically go volume equals to pi. Now you can factorize it, right? Between the limits of 0 and pi on 4. And I'm going to take the y squared on the pink, and I'm going to subtract the y squared on the blue dx. Now, if you're really pedantic, might be worthwhile putting y1 and y2, but I'm just going to use colors to demonstrate the difference, right? So just to be clear, the pink graph is this guy, and the blue graph is this guy, right? I'm going to sub both of those in, right? Sub the blue into here, and sub the pink into here, right? So then I get pi 0 pi on 4, 2 cos x squared minus sec x squared. Now, that's nice because I know sec squared x, this actually combines two questions that I've done today, the two types together. One's double angles, the other one is sec squared, right? So two of these we can hopefully, for you, integrate quite readily, right? Pi on 4, that becomes 4 cos squared, which is, we know the double angle of that, and that's sec squared, right? So once again, I'm going to replace cos squared x with cos 2x plus 1 on 2. That's nice because the 2 cancels out. So let me just pop it there. Becomes zero pi on 4. 2's cancel out, so that becomes 2 outside of cos 2x plus 2 minus sec squared. Okay, now I can integrate all of those elements, right? It's actually quite nice. Oops, I've got no more space. Equals to pi. That now the derivative of 2x is there, so that's just sine 2x plus 2, which is 2x, and that is just 10x pi on 4. Guys, I have no more space below, so I'm just gonna, and 0. Come over here for the final answer. So pi outside of, so sub pi on 4 in, so that's sine pi on 2 because I'm doubling it, plus 2 times pi on 4 minus 10 pi on 4. And guys, when I sub 0 in, I believe sine 0, 0, 2 times 0 is 0, minus 0, 0, 10, 0, 0, right? So now, only values there, that guy there is 1, and that guy there is also 1. 1 minus 1, is that right? Yeah. So the 1's go away, that's like pi on 2, so it becomes pi squared on 2, I believe. Yeah. Units cubed. It's nice. So for this one, I mean, a little bit more intense because you're taking the region that is enclosed by 2 graphs, right? So you basically split them, pink and blue, sub them in separately. Now, don't do the mistake where you sub them in and they have a perfect square out front. No, it's like square over here and square over here, right? What difference are 2 squares, right? Once you do that, sub in the graphs and you integrate it to get the answer. Just remember for this one, sec squared, we have a reference paper equation for that to become 10, while cos squared, double angles. Guys, hopefully that was okay for integration volumes with trig. I am planning another video, which is sort of out of syllabus. It used to be in syllabus, in the 4-unit syllabus for volumes, which uses the method of slicing. Now, the reason why I'm bringing it up is because some schools actually have questions using slicing, right? I thought I'd throw it in there as general theory. If it doesn't apply to you, watch it, learn a new method, but it's extension to what you need to know. Really, it's no longer really in syllabus, but I thought it'd be cool just to do a video on it. If you like that, please hit the like button, subscribe to the channel, and I'll see you at the next lesson. Thank you.